All right, so can everyone load the quantum neural networks notebook? This one should be simpler because you're not really constructing any Hamiltonians. You're just loading the data, you're training it. That's it. Yeah, okay, so does everyone have the notebook with you? Can I get thumbs up once you have the notebook? Okay, I see a few thumbs ups. What about the rest? Okay, please let me know once you have the notebook open. What about the rest of the people? Do you have the notebook open? Okay. Okay, I'm still missing thumbs up from a few more people. Do you have the notebook open?
You can feel free to unmute yourselves as well if that's easier for you than doing a thumbs up.
Yeah, definitely. If you're having any problem loading AWS bracket or anything, you can also let me know. Okay, so I'm going to get started. I'm going to start now. Okay, so actually before I get into the notebook, again, let me give you a little bit of background. You already know like 99% of the background, but the 1% that I need to tell you is something about data loading. So quantum neural networks work exactly like VQE. These are another variational algorithms that use variational principle that you all have learned today. That's why I said variational principle is it's a very strong statement. It's a very strong mathematical statement. Strong in the sense that it can be applied to any optimization problem, essentially. So the way we work with neural networks is usually we have a data. Let's say you have an image. You load this data into a matrix, right? You have complex numbers, you have image, video, anything like that, floating point numbers. And then what you do is you have your neural network, right? Weights and biases. And then there is final loss function. The theta represents the weights, right? So that's classical neural networks. Now, I already showed in my slide before that the idea of quantum neural networks is simply preparing this state psi that is done by applying u of x. So what you do is you actually pass this of neural networks. So when I asked previously, I did get a number of thumbs ups. So I'm going to assume that you have seen neural networks before. Even if you haven't, it's fine, because all that is happening is, let's say I have pictures of cats and dogs, right? Including, let's say, Alex's dog in the picture. And I want to classify whether the picture is, so I'll give it like 1,000 different pictures of cats and dogs. That's called my training data. And I will give it, let's say, 10 pictures of unseen data to this neural network. What happens is when I train 1,000 different pictures, it will essentially try to optimize this theta, a set of parameters that will try to minimize this cost function. Okay, so the goal is to find theta that minimizes this cost function, right? And so that's how classical neural networks work. In the context of quantum computing, it works by first loading the data into a quantum circuit. This is the hardest part. And then you train the parameters of the circuit. And then you compute the cost function like this. Okay, so this is pretty simple stuff. Okay, so I said that the one main challenge with quantum machine learning, quantum neural network, is data loading, which basically means how to load the data into your quantum circuit. We can't really apply random gates, random rotation gates for the purpose of data loading. Here, maybe you can get away with, because this is more of a hyperparameter. You're just trying to find the best hyperparameter possible, right? But this part has to be systematic. So, for example, let's say you have a data, for example, like an image with floating point numbers or complex numbers. I need to prepare to load this data, right? What I'll do is I will prepare the state alpha I, let's say I, okay, where I is just 0, 1, 2, and -1, let's say. So basically, as an example, let's say I have a data set with 4 features, okay? 4 features. Let's say we'll use, in our example, we'll use this iris flower. This is very typical example used in classical machine learning for introductory purposes. We'll use that. So basically, what the data set describes is you look at flowers and you basically measure the following quantities, right? Petal length of the flower, petal width of the flower, then sepal length of the flower, and then sepal width of the flower. Okay. Let's say this is measured in like centimeters or millimeters. Okay, let's centimeters, and let's say this is like 0.1, 0.2. I think that's a bit too small. Maybe let's say 1.0, 2.0, 1.5, 0.5, something like that. Or let's say this is not the data set, and in my data I have a complex number, right? Let's start from like a complicated example as well. So okay, I won't delete this. Let's consider this as an example. Let's say I have another data set with feature 1, feature 2, feature 3, feature 4. And I have, let's say, 1 plus 2.0i, 3 plus 1.5i, so on and so forth, right? Okay. How do I load this into a quantum circuit? So what I would like to do is I would like to load this into my qubits like this, where first of all, what I'll do is I will normalize this. Why do we need to normalize this? I'll tell you now. And I'll load these as amplitudes. Okay, so I'll go to this code. Let's say because there are 4 features, so how many qubits do I need to use to load into the amplitudes of? So how many qubits do I need to load 4 features if I want to write it as an amplitude like this? First, it needs to be normalized. This is not normalized. That's the first step. Can someone tell me how many qubits would I need to load 4 features in this manner? Anyone? 4 qubits? Yeah, that would be one way of thinking, because essentially the state of a qubit would represent, let's say, the value, right? But we actually don't need to use 4 qubits. Actually, we can just get away by using just 2 qubits. Why? Because with 2 qubits, For you need 2 qubits to everyone. Does it make sense? I mean, you need 2 qubits to, yeah. So the reason why you need 4 is, remember that we have qubits n. N qubits have how many different possible states to the n, right? So each amplitude will correspond to each of the state in the 4-qubit system, right? And so I'll need 2 qubits. If I want to load it as an amplitude like this, I would need 2 qubits to load 4 features. Let's say I had 3 features in the data set and not 4. Now what do? Does quantum computing not work in this case if I have 3 features? Because 3 is not 2 to the n, right? What do I do? Exactly. So you pad a 0, right? So let's say x1, x2, x3, and then the other feature will just be 0. Not the feature, but the amplitude will just be 0. So let's say we'll load this as 0, right? So in this manner, any data set of any size, in principle, can be loaded into the amplitudes of a quantum circuit. In particular, 2 to the n amplitudes, right? Okay, this is great because that means I'm able to load the data in a manner that makes sense. Because when I measure the circuit, let's say I load the data, I measure the circuit, the probabilities of each of the corresponding to each of the states will tell me what the features are, right? So if I measure this probability, then this will tell me what the petal length is. If I measure this probability, it will tell me, sorry, right now I have amplitudes, okay? So I'll need to do square root of the probability. Yeah, so that's also important. But the probability will correspond to the amplitude, right? Because it's a square root. So each of the features will correspond to the probability, right? So I'll need to do this. Okay. This is good because now this means that I can load my data into a quantum circuit, right? In a way that actually makes sense when it is measured. Then I know how to interpret the results, right? Because of the reasons specified. However, the question is now how to synthesize a unitary matrix that can load an arbitrary data, right? So because these numbers can be anything, any complex numbers, how do I load this into a quantum circuit, right? I mean, like this is a difficult task. In principle, it can be done, but we have to do it efficiently. Remember that if you use let's say a lot of CNOT gates to do this, then your circuit depth is already too high and noise is going to corrupt your result before even you start training. So this is the problem with quantum computing today. The problem is that it can't load classical data efficiently. It actually requires, even though it's great that to load n data, I only need log n qubits. So this is very good, right? Because in classical case, I would need n data. To load n data, I'll need like n bits. I will need log n qubits. This is good, but to do this, I actually need exponential resource. And I'll tell you how to synthesize this, and you'll see why you actually need exponential resource, okay? I will not get into the theory of it, but I will just mention it because it's very, very important for you to understand, okay? So now let's get into the code. That's all you needed to know to essentially get started with the code. Today, we'll use the penny lane framework. So I don't really have exercise solutions. I just have the code because y'all are not familiar with penny lane at all. So we'll go through this step by step. But penny lane is a great framework to work with differentiable programming or quantum machine learning. Okay. Yeah. Okay. Great. Now, if you look at the code, I think you should be able to run this in the AWS bracket. if you're running this as a notebook, can someone give me a thumbs up if you can load this or not? If you can run it or not load it, sorry. If this can be imported, then that means it should work, because penny lane container has like this penny lane bracket plugin. I loaded in my computer because I can just use pip install penny lane bracket plugin. So it means you can load it locally, but for the purposes now, can someone gives me a thumbs up if you can load this notebook on a bracket? Sorry, run this notebook. Okay, I get a thumbs up. Excellent. Get a few thumbs up. Okay, very good. All right. Okay, so this is great. Now we can actually get started and actually train a quantum neural network. Okay, so I will briefly talk about what each function is doing. This one is the most straightforward. I think this is there's nothing quantum about this. So you have labels, you have predictions. So labels is essentially, okay, so I'll just refer to the data set. If you click on the iris data set, you'll see that it has 5 columns. The first 4 columns are the petal length, petal width, sepal length, sepal width. But the last column are 2 classes, class 1 and class -1. I think these classes represent two different classes of flowers, but they have just been labeled with class 1 and class -1. So essentially what they did is they looked at 2 different flower species. Let's say flower 1 type is class 1, flower 2 type is class with -1, and then they took the measurement data, essentially, right? That's what you're seeing. So label, they basically means my output, okay? So label means by label, I mean output, and prediction is the prediction that I make what the output will be. And the square loss is this function that I want to minimize, because I want to minimize the difference between the predictions and the labels, right? When I'm training my circuit, when I'm training the angles, right? And the way you calculate it is you just take the difference. So what you're doing is you're actually taking the square root of the norm, of the difference of the norm. Sorry, just the difference, and then you just take the norm, because these are just 2 vectors or numpy arrays. A simple way of doing this is you can just do numpy mean. If you want to do like more, traditionally, you can just sum it up and then divide by the length also. It is assumed that the length of these 2 things are the same, okay? So I'll just go back to the previous code. So this is your square loss. Accuracy basically means, here I say that to compute if your code is accurate or not, let's say the label that you predict is like 1, -1, 1, and the prediction is like 1, 1, 1, -1, let's say, right? Then what you do is you would actually, because the predictions are, because the labels are +1 and -1, so will the prediction be. So I'm saying that basically take the absolute difference between these 2 values, and because when you take the difference, right, you essentially want it to be 0, but here I'm putting like a number that is very, very close to 0. Okay. You can also replace this. The reason why I'm doing this is because this is, -1.000000, instead of just -1. So this is basically saying that count the number of cases when I have the difference as absolutely 0, and then sum it up. So the sum counts it, okay? And then I am dividing this by the length of the labels. This is written as a list comprehension. You can simplify this by, you can do something like this as well. Let's say you can do resolved accuracy equals to 0. And then you can say for label and prediction in zip label predictions, which means this iterates to this guy, this iterates through this guy. Then yeah, if this is less than 0, then just add 1 to it. Okay, this is what this list comprehension is doing. But this is like an elaborated form of it. Just comment it out. Okay. Yes, so this is where the data loading part comes in. And here you'll see exactly how to do the data loading. For that, just click on this paper, and it will take you to a new page. Okay, I'll need to share my full screen for you to be able to see. Okay. Can everyone see this paper that I just loaded? Can I get a thumbs up? Okay, see a thumbs up. That means you can see my screen with the paper. Excellent. So remember that I was saying that this data loading part is actually exponential. That is essentially analyzed in this paper. And they say that they're actually improving quantum circuit of this many CNOT gates and this many rotation gates. So, and that is considered like, efficient in a way. So you see that this is exponential number of CNOTs and exponential number of rotation gates. This is for arbitrary case. If you want to load an arbitrary data into the amplitudes that in the manner I just described, you need exponential number of CNOT gates. The technique is basically described here. So what you do is you take your data and then you sum it up in this manner and you take sine inverse of it, and then you run this circuit basically. Okay. So this is just for the reference, and that's what we do in this code. Just to people like who are like, how did we even get this? So this is because someone else has already done it. If you don't want to go through like, any of this, Penny also has an option to do that. So you can just do, you just call qml.amplitude embedding. Yeah, something like this. It's not going to work with this code because I'm loading the angles and then I'm passing that to the state preparation. But you can just pass your features directly to this qml.amplitude embedding, and it is going to load the state directly for you. So you won't have to go through all of this. The reason why I like this here is you can exactly see what is happening, right? Rather than this black box function that prepares the state, okay? So what this does is it takes, because I have how many features? Like column of 1, 2, 3, 4, right? So 4 separate features. It takes 4 features as input, and it actually outputs an array of 5 things because that's what the paper proposes. And then it passes these 5 things in as angles to your rotation gates into the quantum circuit, okay? And this is just the state preparation part. You can see that it encodes 5 input angles using this get angles feature to load it into 4 amplitudes of a quantum state. Okay, so that's our state preparation part. And this layer part is where our U of theta is, or this is where we train our circuit. So there are criteria. So this, I told you that this is like a hyperparameter. You can choose whatever you want to choose to train your model, because data loading is done. This is a hyperparameter that the user can choose. However, whatever you choose, you need to make sure that the depth is not too high because it's going to contribute to the noise. So what we do here is we just apply this single qubit rotation gate so wire, okay, in penny lane, okay, I didn't really go to the grammar of penny lane, which starts here. It should be obvious. RY means rotation Y. Wires means qubit. So C0 gate. Wires means is acting on 2 gates. Rotation Y acting on qubit 1, so on and so forth. Poly X means it's just just the X gate. Okay, bit flip operator. Okay, good. So if you Google QML.rod, which we can do together. So QML.rod is actually going to take you to this file, and you can see that this is a single qubit rotation with 3 angles. You saw this in the block sphere representation. So this is a general single qubit rotation gate, and this is widely used in quantum neural networks. It's a good idea to use this gate because essentially you are sampling, in a way, all across all the points in a block sphere. Not all, but like if you were to take like infinitely many samples, then that would give you the block sphere, right? So you want to make sure that your ansatz, which is the unitary u of theta, is expressible enough that it samples points from all the points in the block sphere. Okay, so that's one property, which is called the expressibility. There is a nice literature, big literature out there, which is important, which we can see is captured by this gate. And the second property, the important property of the ansatz, is entanglement. So we see that we're applying the C0 gate to entangle the first two qubits. Okay. So that's why it makes sense to apply this type of ansatz. Play around with this, like change this rotation 3-qubit rotation gate to this rotation Y, for example, and see how the result changes, which you'll do later. I'll do as well. But that's what's happening in layer. Okay, so once we have this, then we can create our full circuit that consists of the trainable parameter, the input data X, and then so the input data will be passed to state preparation. So actually, it's not input data actually. Input data passed to this get angle function, and then that is passed as X. Okay, so it's not raw data, but rather, let's say, process data, where this is happening. Okay, so this is your input, state preparation. The nice thing with PennyLane is also it has very nice visualizations. So you can visualize a circuit. I'm putting a barrier here, and I'm saying that it's only visual equals to true, which means it's only a visual barrier. You can also set an actual barrier in a quantum circuit where you wait until that point, all the gates have been applied on all qubits. You wait, and then you follow like further instructions. Okay, so this is the purpose of that. If you're running it on an actual device, okay, on a simulator, it doesn't matter. And then what I do is I do layer weights in weights, apply this layer. This basically means that I'm repeating across this layer weights function, layer weights parameter. And this is going to be my list of a rotation angle. So for example, because I'm using 2 qubits, the first dimension is 2. And because I'm using this 3-parameterized single qubit gate or U3 gate, the second dimension is 3. Okay, and if I repeat the layer, then I can create a list of those parameters of these shapes, and I basically repeat the layer. Okay, so what is happening is state preparation. This is your ansatz. And then here I just measure the first qubit. So this is a local function because it's called a local cost function. So one statement I can make for this is when you train your quantum neural networks, I said that noise can cause you barren plateaus, which means you get stuck in local minimums. It's called noise-induced barren plateaus. But even if you had no noise, there is a theory or like analysis out there that tells you that if your cost function is not local enough, then you also get stuck in barren plateaus. So that's called cost function induced barren plateaus, which means make sure that your observable, is not z, but instead z only on few qubits. So here I'm only doing z on the first qubit, and the second qubit is just ignored. Obviously, you can also do second qubit as well because this is just 2-qubit system. But for larger ones, better make sure that your cost function is local. Okay, just something to keep in mind. So the next part is I'm just testing the code. Okay, so let's run it together. I'm gonna put a stop here because I don't want to run anything after this. Let's restart and run the code. And you'll see this nice visualization where you have 2 qubits. All the stuff before the barrier is just for state preparation. And then you'll see here single qubit gate with 3 parameters on both qubits, and then a C0 at the end. And then I applied a barrier for visual purposes, and I'm only measuring the first qubit, right? So Yeah, nice visualization by Penlane. Yeah, so this is just for the testing purposes. You can try other type of input data and it should still work. I hope you're running the code in the background. Okay, so after this, we have this variational classifier function that takes weights, bias, and the input data. Again, so X is not really raw input data, but the input data after passing through the get angles function. And what this does is basically it evaluates the cost function, and I'm also adding a bias there. Actually, you can also try not adding this bias and see how the result changes. The purpose of adding this bias is essentially adding another trainable parameter. Okay. All right. And then my cost function will be basically this classifier circuit applies on weights, biases, and my input data. And then that will be my predictions, but my cost function is the difference between the predictions and the true value, which is y. Okay, the true labels, which is in this data here, this row. Very good. So after that, I have a test preparation circuit that I have. Again, so this test is to make sure that the code runs correctly. And you can print it out and you'll see that the input data has 4 features. I mean, it's of length 4, but the angles will be 5 because of this get angle function that I mentioned earlier. And then, see a question, comment for a training that, okay, so Pawsey hosted a playlist training for Penny Lane.
Yeah, so just there is some Penny Lane training available. You're referring to Penny Lane quite a bit.
Yeah.
So that's free for everybody to go have a look.
Okay, thank you, Anne. And then once this angle is passed, I'm getting my state vector here. So when you do QML.state, it actually does like a full state vector simulation because this is just for the purpose of test. Okay. What I'm doing here is you'll see that I have this wrapper at QML.QNode. So you need this for any circuit that you define, this wrapper with the device. So in this case, my device is just default.qubit. Now I'll tell you later how to run this on AWS, what device to use, but for now, yeah, you can just use this. Okay, excellent. So after this, we do some data pre-processing. So data is just, you just load this data set, and then you load the features of this data for each row, get the features from 0 to second column. Look at the data set. So I'll skip this because this is just the pre-processing part. Please read through this to understand exactly what is going on there. There's been like a bunch of padding and stuff to make sure that the dimensions align. Here I have a function that does that plots the the raw data. Okay, and this is the visualization. So okay, so let's just run everything. Okay, so this is how the input data looks like. So this was our original data, right? And we can see that there is a clear segregation between these two classes. Based on, so here I have plotted the first, let me see. So here I have plotted the first dimension, which means this guy. So basically this is probably like pedal length or something, the first feature. Okay, so I have plotted the first feature of the original data. Remember that I'm doing this with, sorry, here it's here. Yeah, first feature of the original data. I'm doing this for labels 1 and levels -1 here. Sorry, labels 1 here. And then labels -1 here. And I'm doing a scatter plot between the first and the second feature, which means maybe pedal length and pedal width, for example. And my class 1 is labeled blue color, and then the -1 is colored red. Okay, and that's what I'm doing with the first plot. The second plot is after I did the padding and normalization, because the vector in a quantum state has to be normalized because of the thing that I mentioned. So after padding and normalizing, this is just making sure that the classes are still segregated, which is what we see. That is expected. And then this is after getting the angles. You'll see that after you run the angles, the classes are still segregated. We did a very systematic selection of angles with the arc, sine, inverse, and all that. And you can see that it is systematic because it's not changing anything. The classes are still segregated. Okay, so this is good. So after this is all a bunch of pre-processing stuff. So here, in classical neural networks, in machine learning, you always split your data into training set and validation set. I create 75% of input data as my train indices, and then the rest of them as validation indices. I do the same thing with the features and the label. Okay. So this indices will be passed here. This is basically dividing your data set into 75-25. That's all I'm doing. I'm doing this for features as well as labels. Remember, features are the first 4 columns and label is the last column, okay? Which tells us what kind of flower it is. Okay, very good. So yeah, so some important things here. Yeah, I'm using 2 qubits. Number of layers is, let's see, pretty standard split between training and validation sets. Yeah, but I think like it's again a hyperparameter, right? It's up to you to like do 80-20. You can even try doing 60-40. Yeah, in this case, we just chose to do 75. Yeah, so standard, but not really standard because like it's really up to you to choose. Okay. The other thing is I want to make sure that, so here I am using 6 layers, right? So 6 layers of, yeah, so 6 layers is the number of layers of my this part, the u of theta, the trainable u of theta. Okay, so in this case, I was just using 1, remember, right? In this case, I have used 6 of them. Actually, let's just do like 2. 6 is a lot. So here I'm initializing the weights, biases. Okay, it's just a single number. Yeah, and then here I am repeating this 60 times with this Nesterov momentum optimizer. The nice thing about Penny Lane is they have like these inbuilt optimizers that we can use easily. There are gradient-based optimizers, gradient-free optimizers that work very well with these quantum circuits. Okay, and so I'm repeating through these, and I'm also creating batch sizes, which means I'm creating 5 batches of my data. So I'm dividing it into 5 parts, and I'm training them in batch. This is also another typical step used in machine learning. You can try not using any batches at all and just train them at once. Anyway, so that's all that is going in on the plot. And then here I will plot my cost function, my accuracy, and then here you'll see the result. Okay, so let's run this. So here, okay, let me just start from what I had. So I'll run with 6 layers, okay? So let's run it with 6 layers. Let's look at the plot. After 60 steps, what happens? Okay, so the cost function, it gets closer and closer to 0. Okay, so that means that the training worked well. Okay, now let's look at the train and the validation accuracy. Okay, so the training accuracy is also close to 100%. And so is the validation accuracy. And this is what you like to do when you're doing machine learning, right? So not always the case, but because it's a simple example, it worked out. Okay, and here I have like this code to plot, basically plot this training data, training labels, validation data, and validation labels, and given your input train weights and train biases. So these are our optimal weights and optimal biases that are passed to this function, and this function basically plots the following. Okay, and it looks like it worked out correctly, right? So class 1 train is represented by circles. Validation is represented by triangles. 1 corresponds to the blue color and -1 corresponds to the red color. And this line is essentially like our classifier line that separates these two things. And we can see that these are separated with almost 100% accuracy for both training and validation data. Okay, now I said your turn. So try changing the number of layers. Okay, so try changing this from 6 to 2. See how it does. Okay, let's run again. And let's start from here. Okay, so the loss function doesn't really converge to 0. But it still is reducing-ish. Okay, yeah. So the trade validation accuracy is going up and down. Yeah, and okay, so it's very bad. Okay, so maybe don't use 2. Why did it not work out? It basically means that we still don't have sufficient parameters to be able to train this model, train on this data set. Okay, so with 2 layers, that means I only have 6 parameters, essentially. Okay, so maybe try like 4. So remember, I told you that the ansatz needs to be expressible enough. But it's also true that if you have like sufficient number of parameters, not too high, because that's also gonna cause problems. You're gonna hit local minimums. You should be able to parameterize, any data set. That's the idea of like neural networks, right? Or LLMs, like with these like trillions of parameters. During the inference, it's able to basically, you ask a question and it can output you things and predict like the next word, right? During the inference. So basically, given a sufficiently large number of parameters, you can essentially approximate any function. I think it's called universal approximation theorem or something like that. Obviously, like doing that in practice is difficult, but in theory at least. Okay, so I tried 4 layers, and it looks like, yeah, so it looks like 4 layers seems to suffice to essentially separate it out. Maybe not absolutely 100% accuracy, but I mean, this is close to 100. Okay, so play around with the number of layers. The other things you can also change is try changing this ansatz circuit. Okay, so here I had the 3-qubit rotation gate. Just try applying like a single qubit, not 3-qubit rotation gate, single qubit rotation gate with 3 parameters. Okay, so how about we just do like only apply it on the first qubit, right? So like, let's say 0 and 0 or something like that. Okay. So this basically means that I'm only applying on the first qubit. Yeah, see. And okay, so this doesn't work that well. Yeah. So yeah, please feel free to play around with this. And I'm way over time. So with this, I'll wait for any questions. Okay, can I get a thumbs up if you have been following along? Okay, I see a few thumbs ups. Okay, great. Okay, so I see a number of thumbs up. All right, excellent. Yeah, so with this, I will end the lecture here. Why is batching the training beneficial? Okay. So if you actually do batching of your data, so basically divide your data into batches. So first of all, what you need to understand is that, yeah, no, it's fine. It's more of a machine learning question, right? Yeah, I don't really have a very good background in machine learning, but my understanding of it is that it helps you train easily, in the sense that if you do it in batches, then you essentially have less data that you're loading at a time.
You normally use batch processing for your ML pipelines, and this is true for any ML or quantum machine learning pipelines when you have a large volume of data. If you if your batches are small, it's going to take a really, really large time for you to process all your data. And so batching is there to help you process really large volumes. And so what this means is that this process allows you to scale up your machine learning pipelines, your machine learning workflows, especially when you have to deal with like massive data sets, extremely high dimensional data sets. And yeah, it's more of a time versus efficiency type of thing. If each batch only has if each batch only has you go through each batch one by one. If each batch is basically your entire all your data, it's going to take a really, really long time to train. And so and in the end it's an efficiency thing. So yeah. Okay.
Yeah, so just keep in mind that if you don't do any batches, then it could take you very, very, very long to load a large volume of data. Yeah, thanks, Jonas.